Hello everyone, this is the second part of numerical analysis objective exercise. So let's get started. The first objective question is, which of the following is an example of Gaussian quadrature formula for numerical integration? And our options are A. Trapezoidal rule, B. Simpson's 1 by 3 rule, C. Simpson's 3 by 8 rule, yeah, or D. Gauss-Lagrange quadrature. So you can pause the video and guess the answer. So the correct answer is the the Gauss-Lagrange quadrature. And let's understand why with example. Why? So Gauss quadrature is a method of approximating definite integrals, basically finding the value of definite integrals, using a weighted sum of function evaluation at specific points within the integration interval. So what is Gauss-Lagrange quadrature formula? It is a specific instance of quadrature, Gaussian quadrature, that uses Lagrange polynomial as a basis function. So Gauss-Lagrange formula is defined as follows. That is integration from a to b f of x dx, which is approximately equal to b by minus a by 2 multiplied by summation of where from I is equal to 1 to n wi multiplied by f of xi, where a and b are the b are just intervals of the integration, fx is integral function, n is the number of quadrature node, and xi are the quadrature nodes, whereas the wi are corresponding weights. So the Gauss quadrature nodes xi, the xi in the Gauss-Lagrange formula are chosen as the roots of the nth order Lagrange polynomial Pnx or f of x. So the Lagrange polynomials have that property that they are orthogonal over the interval -1 to 1 with respect to the weight of the function wx is equal to 1. This is orthogonal property allows for accurate integration of the polynomials. By selecting the quadrature nodes as the roots of the Lagrange polynomial, the Gauss-Lagrange formula provides the best approximation of the polynomial of degree 2 by n, 2n minus 1 or lower, 2n minus 1 or lower. Remember it, it provides best approximation for polynomials of the degree 2n minus 1 or lower. So the weights wi in Lagrange formula are determined in such a way that formula achieve exactness for the polynomial up to the degree 2n minus 1. Therefore, the Gauss-Lagrange formula satisfies the criteria of being Gauss quadrature as it integrates the polynomial up to a certain degree using Lagrange polynomials as a basis function. Okay, so as simple as that. Now let's jump on to the next question. So the next question is, which of the following is true regarding the weights and abscissas used in the Gaussian quadrature formula? So the weights and the abscissas are equal in number. The weights and abscissas are not equal in number. C, the weights and abscissas are same for all order of the formula. Or D, none of the above. So you can pause the video and guess the answer. So the correct answer is A. The weights and abscissas are equal in number. Let me give you an example and prove it. Let's say take an example of Gauss-Lagrange quadrature as we discussed earlier in first question formula to explain the relationship between weights and abscissas in the Gauss quadrature. In Gauss-Lagrange quadrature formula, the abscissas are chosen as a root of nth order of the Lagrange polynomial and denoted as a Pnx. And these abscissas are denoted as xi. So how do we calculate the weights in Gauss-Lagrange formula? Weights is denoted as wi, by the way. So how weights is calculated? The formula is given here. Wi is equal to 2 divided by 1 minus xi square, p dash n xi whole square, where p and xi represents the derivative of nth order Lagrange polynomial, which is evaluated at the abscissa xi. Fine. So putting the value of x, we can get the specific weight of that weight at the particular abscissa, and using this weight and xi, it will help us to approximate the definite integral function, right? So let's consider a specific example, Gauss-Lagrange quadrature with n equal to 2, which means we are using two abscissas and weights. The root of the second order Lagrange polynomial p2x are minus the square root of 1 by 3 and square root of 1 by 3, as we all know. So for n equal to 2, we have two abscissas. x1 is equal to minus the square root of 1 by 3 sorry, and x2 is equal to square root of 1 by 3. Similarly, we can find their corresponding weights by the formula we discussed earlier, that is wi is equal to 2 divided by 1 minus xi square multiplied by p dash n xi whole square. So using this formula, we will find W1 and W2, and by evaluating the derivative of second order Lagrange polynomial and substituting the value, we can calculate the weights more precisely. So for this specific example, if we calculate the weights W1 and W2 respectively, the answer we will get will be W1 to be 1.000 000 and W2 to be 1.000 Here we can see that number of abscissa is equal to the number of weights 2 in the Gauss-Lagrange quadrature formula. The relationship holds for all Gaussian quadrature formulas. The number of abscissas and weights is always equal, ensuring well-defined, accurate approximation of the integral of definite integral for all the quadrature formulas. So just remember, keep in mind for that, for all the Gaussian quadrature formula, the weights and abscissas will always be equal. Okay, so let's jump on to the next question. Our next question is, what is the accuracy of Simpson's 3 by 8 rule? So our options are A1, B2, C3 and D4. So the correct answer is C3. Why is it that? What is it that the actually basically what is the order of accuracy? Order of accuracy means that the rate at which approximation method converges the exact solution as a step size, which is basically the number of integrals as the step size decreases. So it converges as the number of integrals decreases. In case of Simpson's 3 by 8 rule, it is a numerical integration method, and it will help to approximate our definite integrals, which is basically finding the value of definite integral at a particular interval. Okay, so the order of accuracy for Simpson's 3 by 8 rule is 3, which means the error between the exact solution and approximation decreases at the rate of OH to the power 3, where h is the step size. This indicates that you decrease the step size, the error decreases significantly faster compared to the lower order methods. The error in Simpson's 3 by 8 rule is proportional to h to the power 5, but the dominant term is h to the power 3, leading to the third order accuracy. However, the truncation error in the Simpson's rule is minus 5 to the h to the power 5 by 90 into fourth order derivative of f of 0. So this is the truncation error in Simpson's rule. Now, how to calculate the truncation error in Simpson's rule, we will understand in detail in the next video. So stay tuned for that. Right now, just remember that accuracy of 3 by 8 Simpson's rule is 3. So let's jump on to the next question. Next question is, which of the following is an example of composite integration method? A. Trapezoidal rule, B. Simpson's 1 by 3 rule, C. Gauss-Lagrange quadrature, or D. Both A and B. So the answer is obviously both A and B. What is the question? Again, trapezoidal rule and Simpson's 3 by rule, they both are, yeah, so trapezoidal rule and Simpson rule are the examples of composite integration method. So let's see what is composite integration method. So composite integration method is a technique used to approximate the definite integrals. As simple as that. It also gives the value of definite integrals. But what is the meaning of composite here? So basically, it helps to approximate definite integrals by dividing the integrals, dividing the integration interval into smaller subintervals and applying an integration rule within each subinterval. Okay, so the basic idea is to approximate the integral over each subinterval and then combine the results to obtain an approximation of the entire interval. Okay, so the trapezoidal rule is commonly used composite integration method. It approximates the integral by dividing the interval into series of equally spaced intervals and approximating the function as a straight line within each subinterval. The integral is then computed as a sum of areas of the trapezoids formed by connecting adjacent points on the function, as we can see in the graph here. it has been divided into several trapezoidals, and then we will add the trapezoidal. So area will be equal to integration from a to b y dx, which is approximately equal to 1 by 2 h in the bracket y0 plus 2 y1 plus y2 plus y3 up to the yn minus 1 plus yn, where h is equal to b minus a by n. So basically this is the example of trapezoidal rule, and it is also the composite integration method. As we see, it has been divided, the interval is also divided into very smaller subintervals, right? Now Simpson's 3 by 1 by 3 rule is another composite integration method. It also approximates the integral by dividing the interval into many subintervals and chota chota karna hai. Many subintervals they are dividing and then adding them together. Okay, and approximating the function within each subinterval using quadratic polynomial. So the catch is that it uses quadratic polynomial concept here. Okay, so the integral is then computed as a sum of areas under this quadratic curves. There we were thinking about trapezoids. Here it is quadratic curves. So it is integration of a to b f of x ds, approximately equal to the delta x by 3, f of x naught plus 4 f of x1 plus 2 f of x2 up to the 2 f of xn minus 2 plus 4 f of xn minus 1 plus f of x minus xn, where delta x is equal to b minus a by n, which we can also write h here instead of delta x, as we have written in trapezoidal rule. And x naught is equal to a and xn is equal to b. They are the limits from a to b, integration limits, and are the ends of n subintervals, right? Error bound is m b minus a to the power 5 divided by 180 n to the power 4, where f of 4x is less than equal to m. So basically this is the Simpson's rule. In the same way it is as a trapezoidal rule. It is also an example of composite integration method, where integral is approximated by dividing it into more subintervals and then approximating the function. So let's jump on to the next question. Next question is, what is the drawback of using high order Newton-Cotes formula for numerical integration? So our options are: A, they are less accurate than lower order formulas. B, they require more functional evaluations. C, they are not applicable to non-smooth functions. Or D, none of the above. You can take your time and guess the answer or pause the video. So the correct answer is they require B, they require more function evaluations. So why they require more functional evaluation? So Newton-Cotes formula are a class of numerical integration, which it also approximates the definite integrals by evaluating the functions at a set of equally spaced points with an integration interval using weighted sum of these functional values. Okay, so higher order Newton-Cotes formula such as Simpson's rule, extended midpoint rule, use even more evaluation points and thus provide an accurate approximation of the integral. However, a disadvantage of this higher order formula is that they require more functional evaluations. The increased number of functional evaluation can result in increased computational cost and the time. And as we already discussed in key point video, that sometimes we have to balance out the things, that what is the priority. The computational cost is a priority or accuracy is our priority, right? So especially for complex or computationally expensive functions, the increased number of these evaluation will increase the cost, obviously, and also the time. In some cases, additional evaluations may outweigh the benefit of increased accuracy, right? So as we already discussed, this is basically how we discuss the reason behind why so heavy calculations, why so much more requirement for functional evaluations. Now let's get on to the next question. Which of the following is true regarding the abscissas in Gauss-Lagrange quadrature? So they are equidistant, they are non-equidistant, they are dependent on order of the formula, or D, none of the above? So the answer is A, they are equidistant. We already discussed Gauss-Lagrange formula, so let's jump on to the next question. So our next question is, which of the following is an example of open Newton-Cotes formula for numerical integration? So our options are A, trapezoidal rule, B, Simpson's rule, Simpson's 1 by 3 rule, C, Simpson's 3 by 8 rule, or D, both B and C. So what is an example of open Newton-Cotes formula? There are two types of Newton-Cotes formula. There is one open Newton-Cotes formula and closed Newton-Cotes formula. So what are the example of open Newton-Cotes formula? So the answer is B and C, Simpson's 1 by 3 rule and Simpson's 3 by 8 rule. Both Simpson's rule are an example of open Newton-Cotes formula, and trapezoidal rule is basically closed Newton-Cotes formula, example of closed Newton-Cotes formula. So open Newton-Cotes formula for numerical integration are a variation of Newton-Cotes formulas, and that do not include the use of endpoint values of the integration interval. So basically that is a concept of inclusiveness and exclusiveness, right? So in these formulas, the interval is divided into equally spaced subintervals, and the functional values are evaluated in interior points excluding the endpoint, right? So in trapezoidal rule, on the other hand, is an example of closed Newton-Cotes formula, where the functional values are evaluated at both the endpoints and interior points of the interval, right? And then Simpson's 1 by 3 and 3 by 8 rule, which are examples of open Newton-Cotes formula, because they only use functional values at interior points, not ending points, only in interior points. So in Simpson's 1 by 3 rule, the interval is divided into subintervals, and functionals are evaluated at the endpoints and midpoints of each subinterval. And in Simpson's 3 by 8 rule, a similar method which uses some additional functions at the evaluation and two internal points within each subinterval. So basically, trapezoidal is closed Newton-Cotes formula, and the Simpson rules are open Newton-Cotes formula. This is it. The key distinction is open Newton-Cotes formula do not rely on functional evaluation at the endpoint, making them useful when functional values at the endpoint are unknown or unreliable. So this is the difference between open Newton-Cotes formula and closed Newton-Cotes formula. We have discussed their difference, and we have discussed what are examples of open Newton-Cotes formula and closed Newton-Cotes formula. Now let's jump on to the next question. Question number 8. What is the forward difference operator? A, it approximates the derivative of a function using value of a function at two neighboring points. B, it approximates the derivative of a function using values of the function at three neighboring points. C, it approximates the derivative of a function using values at a function at four neighboring points. Or D, none of the above. So guess your answer. What is the forward difference operator? Basically, we have discussed some of these things in interpolation video. So guess, imagine, take your time. So let me give you the answer now. The answer is A, it approximates the derivative of the function using values of a function at two neighboring points. Okay? So this is the use of forward difference operator. So the forward difference operator is denoted by a triangle symbol, and it is a numerical approximation technique, and it is used to estimate the derivative of a function at a specific point. So it calculates the difference of a function at two neighboring points and then divides the difference in their x coordinate to approximate the derivative. The formula of a forward difference approximation is given as follows. After x is approximately equal to f of x plus h minus f of x divided by h. Here f dash x represents the derivative of function fx, and h represents the step size or the distance between the two neighboring points. So the option A accurately describes what is the forward difference operator, and it approximates the derivative of a function using values of a function at two close neighboring points. And we use this in forward difference interpolation. What is the backward difference interpolation? What is the backward difference operator? It is an operator which we use in for backward difference interpolation. Okay, coming to the question. So what is that? What is backward difference operator? And our options are: A, it approximates the derivative of a function using the values of a function at two neighboring points. B, it approximates the derivative of a function using values of the function at three neighboring points. C, it approximates the derivative of a function using values of a function at four neighboring points. Or D, none of the above. It is so obvious question, guys. It's so obvious. The answer is A. It approximates the derivative of a function using the values of function at two neighboring points, obviously, but obviously it is similar to forward difference operator. So here we will discuss a few things about it. So it is upside down triangle. It is denoted as an upside down triangle. So the backward difference operator is a numerical operation technique used to estimate the derivative of a function at a specific point, similar to the forward difference operator. It calculates the difference between the function's values at a point and its preceding neighboring point, divides it by the difference in x coordinate to approximate the derivative. So what is the formula? Let's see the formula. Formula is f dash x approximately equal to fx minus f of x minus h divided by h. Here f dash x represents the derivative of a function f of x and h represents the step size of a distance between two neighboring points. So when we are using the forward Newton's backward interpolation technique, we use this operator to find the value of y, value of a function at a particular point x, which is to the left side of a given point x and given value of fx at that point, right? So it is helped to shift the x to a value. It helps us to find the value of x, which is just at the backside, of the given point, given data, right? Similarly, in case of forward difference operator, it helps us to give the data of the value which is just at the right side, just at the forward side of the given x, right? Jumping on to the next question, that is it. Jumping on to the next question, what is the divided difference operator? So the divided difference operator, our options are: A, it is used to approximate the derivative of a function at a given point. B, it is used to interpolate a function at a given point. My god. C, it is used to approximate the derivative of a function using the value of a function at multiple neighboring points. Or D, none of the above. So you can pause and check your answer. So let me give you the correct answer. So the correct answer is C. It is used to approximate the derivative of a function using value of a function at the multiple neighboring points, right? So why is that? Let's just check it. So divided difference operator is typically denoted by the symbol either normal triangle or upside down triangle, okay? Delta or upside down delta. It's a mathematical tool used in numerical analysis to approximate the derivative and interpolate the function. It is used in divided difference interpolation basically, where the data is not equally spaced. The distance between the points are not equal for each given data points, right? So unequally spaced data points, if there is unequally spaced data points and we have to use the interpolation, we use divided difference interpolation, and for divided difference interpolation we use divided difference operator. It is specifically used to approximate the derivative of a function using values of a function at multiple neighboring points. The divided difference operator is commonly used in Newton's divided difference. I already told you that, right? So basically what it does, it constructs the interpolating polynomial that passes through the given set of data points. So this is basically its work. For the function fx with the data points x0, f of x0, x1, f of x1, up to the fxn, f of xn, these are the data points sorted in ascending order of x, and the divided differences can be recursively calculated as 0 divided difference f of x0 is equal to f of x0. First divided difference for x0 and x1 will be f of x1 minus f of x0 divided by x1 minus x0. F of x1 x2 will be equal to f of x2 minus f of x1 divided by x2 minus x1, and so on. And similarly, we will find second divided differences. For second divided differences, for the points f of x0, x1, x2 will be equal to f of x1, x2 minus f of x0, x1 divided by x2 minus x0, and we can basically use substitution method and finally find the values of this uh, forward divided difference operations. So, and this pattern goes on, and the pattern continues for higher order divided differences. So now let's jump on to the next question. That is it for divided difference. So the next question is, what is a shift operator? Basically, that shifts our point that is used to shift our operation. We have to find the value at x. We have to just shift the value from x. This is work of shift operator. So basically, our options are A, it shifts the value of a function to the left or right. B, it approximates the derivative of a function using the value of a function at multiple neighboring points. C, it used to interpolate the function at a given point. Or D, none of the above. Basically, by mistake, I already have given you the answer, but still, you can guess if you still not get it. So the answer is A. It shifts the value of a function to left or right. So the shift operator shifts the value of a function by a certain amount to left or right. It is denoted by delta x, okay, or delta h, and it is used to represent the horizontal shift in the domain of a function. Horizontal shift, it's not a vertical shift, it's just a horizontal shift. By applying the shift operator to the function, the values of functions are moved horizontally along the x-axis. So, okay, yeah, the shift is along the x-axis, guys. Okay, it's along the x-axis. So the positive shifts of the function is to the right, and negative shift is to the left. For example, if we have a function fx, we can apply the right shift by delta x units, and shift the function would be denoted as, and that shift function will be denoted at f of x plus delta x, and it represents the original function shifted to the right by delta x units. Similarly, we can give for left shift operator, that will be f of x minus delta x, representing the function as shifted to the left by delta x units. Okay, so shift operator is commonly used in mathematical operations using the transformation of the function, discrete time series analysis, and signal processing. So that is it for shift operator. Now let's jump on to the next question. So what is the order of accuracy for Simpson's 1/3 rule? Again with accuracy questions. So the options are A1, B2, C3, D4. So guess our answer is B. Guess what? Answer is B. That is 2. The order of accuracy for Simpson's 1/3 rule is 2. This means as the number of subintervals used in approximation increases, the error in approximation decreases at the rate of approximately h to the power 2. And previously we have 3/8 rule where it was h to the power 3, but here it is h to the power 2, where here h is the width of the subinterval and error decreases quadratically with the number of subintervals. Okay. It is similar to how we understand the accuracy in Simpson's 3/8 rule. Similarly, in Simpson's 1/3 rule, the accuracy is 2. So next question, which of the following numerical integration method is based on the forward difference operator? Trapezoidal rule, Simpson's rule, midpoint rule, or none of the above? You can guess your answer. So the answer is D, none of the above, because they were not used to, they are specifically not used, they are not used for this task, right? The numerical integration method based on use of forward difference operator is known as forward difference approximation or forward difference method. We use forward difference operator for that, but it is not specifically associated with these trapezoidal, Simpson, midpoint rule, because forward difference operator is commonly used in numerical differentiation, okay, to approximate the derivative of a function, but it is not directly related to these particular integration method. So there is obviously so much difference between differentiation and integration. Don't get confused. These methods are not related to integration, right? They are not particularly related to integration. They are forward difference is not particularly related to integration, but these methods are totally used for integration purposes, for finding the approximate value of these definite integrals, that is far different from forward difference operator. Right? That was also an obvious answer. Coming to the next question, question number 14. Which of the following numerical integration method is based on the use of backward difference operator? Our options are A. Trapezoidal rule, B. Simpson's rule, C. Midpoint rule, or D. None of the above. As again, it is but obvious answer. What you can guess the answer very easily. But again, I am going to give you the answer. So the answer is yes. The answer is D. None of the above. None of the above mentioned methods, that is trapezoidal, Simpson rule, midpoint rule, all these rules, as we all know, they are basically used for integration. Backward differences for differentiation, they are totally different. Backward difference operator is used in numerical differentiation to approximate the derivative of a function, particularly when the function values are given at an equidistant point in a reverse order. Okay. However, it is not directly associated with numerical integration method mentioned in the above provided answer. It was so easy, bhai. It was just a copy of another question with just another integration method. Damn. Let's jump on to the another question. Which of the following integration methods is based on the use of central difference operator? A. Trapezoidal rule. C. B. Simpson's rule. C. Midpoint rule. D. None of the above. It is also very obvious. Please guess it correctly. Don't do it wrong. Please. Naak nahi katwani meri. So the answer is D. None of the above, as usual. Because the above mentioned options are specifically based on the use of central difference operator. The central difference operator is commonly used in numerical differentiation. Again, differentiation and integration differences. Okay, so it is used for numerical differentiation to approximate the derivative of a function. It involves taking the difference between the function value at a point slightly before and after the point of interest, right? That is a point of interest. We have to take the difference between the points A and B, and our point of interest will be in the middle of A and B. Okay. So, however, in numerical integration method mentioned in the above options are not more reliable towards the central difference operator for their calculations. Trapezoidal rule approximation is used to integrate the integrals using the trapezoids. Simpson rules use quadratic interpolation, and midpoint rule utilizes the function evaluation at midpoint of subintervals. So they are so much different. Therefore, the answer is D. None of the above. Now let's jump on to another question. None of the The next question is, which of the following numerical interpolation formulas is based on the use of divided difference operator? A. Newton divided difference formula. B. Lagrange interpolation formula. C. Hermite interpolation formula. Or D. None of the above. So you can answer it. Anyone can answer it. Who have never ever heard of interpolation, they also can answer it. What is the answer? The answer is but obvious, A. Newton's divided difference formula. Next question. Which of the following numerical interpolation formulas uses polynomial interpolation? Newton divided difference formula, Lagrange interpolation formula, Hermite interpolation formula, or none of the above. Here I have to explain this answer. So the answer is B. Lagrange interpolation formula. How Lagrange interpolation formula? Lagrange interpolation formula uses the polynomial interpolation to approximate the function based on a given set of data points. It constructs the polynomial to pass. It helps construct one polynomial that will pass through these data points using a series of basis polynomials. These basis polynomials are combined with appropriate weights to form a final interpolated polynomial. So Newton divided difference formula, on the other hand, is different method to interpolate. It is explicitly used for polynomial interpolation. It employs divided differences to construct the interpolating polynomial. Whereas Hermite interpolation formula is an extension of Lagrange formula that allows the interpolation of both the function values and derivative at a given data points. Like Lagrange formula, it also utilizes the polynomial interpolation. But our answer is Lagrange interpolation formula because it used to approximate the function based on given data sets, and it constructs then a particular polynomial which will pass through these data points uh, by using a series of basis polynomials, right? Okay, so let's jump on to the next question. Next question is, which of the following numerical interpolation formulas is used for interpolating a function with both its values and derivative at a given points? So A, Newton's divided difference formula, B, Lagrange interpolation formula, C, Hermite's interpolation formula, or D, none of the above. So our answer is, it's not but obvious, we have not discussed this question. So let me briefly introduce and explain this question and briefly introduce a new concept. So the answer is obviously C, Hermite's interpolation formula. So what is Hermite? Basically, it's used for interpolating a function with both its value and derivative at a given point. Okay, it is an extension of the Lagrange interpolating formula, which only uses a function at a given point to interpolate the function. Okay, it not only the values of a function but also the values of its derivative up to a certain order can be used to construct the interpolating polynomial, which will pass through these data points. An appropriate choice for interpolating a function with both its values and derivative at a given points are that to not take derivatives into the account, so they are not appropriate for this task. Only Hermite interpolation take derivatives also in account while interpolating the data. So that's why here the answer is Hermite's interpolation formula. Okay, to understand in more detail Hermite's interpolation formula, comment down below. We will make a separate video for Hermite's interpolation formula, right? Coming on to the next question, we have, which of the following is true for numerical integration methods based on higher order polynomial? A, they are more accurate than those based on lower order polynomials. B, they are less accurate than those based on lower order polynomials. C, they are equally accurate as those based on lower order polynomials. Or D, none of the above. So the answer to this question is A, they are more accurate than those based on lower order polynomials because of the obvious reasons we all know. Now the next question is, Jacobi method is also known as, name them yaar, another name. What's it from? Okay, so A is displacement method, B is simultaneous displacement method, C simultaneous method, or D diagonal method. So these are our options. Which is the correct option? You can guess the correct option, pause the video and give the answer. So the correct answer is simultaneous displacement method. It is the Jacobi method is also simultaneous displacement method. In this we just make the matrix, we make the matrix diagonal matrix non-zero and make all the other elements, all the other points of the matrix is zero, and then we calculate the values of x1, x2, x3 or linear polynomial, right? So this is the end of our exercise grind, MCQ exercise grind or numerical analysis, which are very basic MCQ questions. If you have any doubt, you can comment down below. Thank you so much.